It's really a very simple idea. Computers ought to be useful for almost everyone, from elementary school to non-computer specialist professional, for very many different purposes. Everybody knows that computers should be useful for programming and using programs written by other people, but text manipulation is also important. One shouldn't forget keeping large amounts of data and retrieving them at will. For example, one might want to keep a personal journal or diary. Any modern computer system must be a communicator as well, and a mail-in message system is necessary. Now, what we expect to get by combining all these functionalities is more than just the sum of the parts. We want a new kind of dynamic and interactive medium. The real problem in this project is one of coherence. One needs to create a system which is perceived by the user as a whole and is incrementally learnable in the sense that a beginner starting in any one of these function areas can move easily to any of the others.
The key to making Boxer, on the one hand, general purpose, and on the other hand, integrated and coherent, is that the entire system is organized around two fundamental principles. The first principle is concreteness. Anything that you see on the screen, whether it was typed by the user or typed by the system, whether it's text or data or programs or whatever, can always be manipulated in exactly the same way. So for example, in Boxer, there's no special editor, and there's no file system, and there's no program entry mode. Rather, if you want to access some information, you go to where it is on the screen, and you look at it. If you want to change it, you change the way it appears on the screen. The second principle behind Boxer is what we call the spatial metaphor. When you build things in Boxer, you organize them using structures called boxes. These are visible regions on the screen, and a user accesses different parts of the system by moving a cursor in and out between these boxes. Our intent here is to allow people to understand the system in terms of common sense notions about moving around in space. The interesting thing about Boxer is how many of the different functions of computer systems are subsumed by just these two very simple ideas.
Our current implementation of Boxer runs on a Lisp machine, which is a high-performance personal computer with a graphics screen and a pointing device. I'm going to show you what it's like to write some simple programs using Boxer. The lower part of the screen is the actual Boxer environment we will work in. This part up here is reserved for graphics, and we do our graphics using a turtle, which is a method of drawing invented at MIT as part of the Logo computer language. We move the turtle using the command called forward. If we type forward and hit a help key, Boxer tells us that we need to specify one input to forward, which is the number of steps the turtle should move. Let's say 200. Now we can mark this command line and then execute it, and the turtle moves forward. We use the right command to turn the turtle, and once again Boxer tells us that we have to provide an input for right to specify the amount of turning. Let's say 90 degrees. Now we mark the second command line, execute it, and see the turtle turn right. One of the basic principles of Boxer is that anything we see on the screen is available for us to use. As an example, we can go back and re-execute the forward line simply by moving the cursor there, marking the line, and re-executing it. And we could do the same thing with our second command line. One way to think of what we have here is a menu of two commands from which we can select and execute, just like the menus in many graphics-based systems. But notice that we didn't have to invoke any special menu creation operations. In fact, what we have here is more flexible than a menu, because we can go back and edit the command lines. For instance, we can change the forward 200 to a forward 300. and then execute that. Let's add another command to our menu to let us clear the screen. Another thing we can do with commands on the screen is to group them using boxes. For instance, we can draw a box around the forward and the right, mark the box, and execute it. And we see the turtle go forward and then right. Let's clear the screen again, and then ask Boxer to repeat this forward-right pair 4 times. This is a simple way to draw a square. Now we can draw a box around the entire repetition. And then give this box a name, like square. Then we can clear the screen again and run square just like any other command. In fact, what we've just done is to define square as a procedure. But notice that we didn't enter any special procedure definition mode, like in most other computer languages. Instead, we just assembled square out of stuff that was already on the screen. We call this style of work concrete programming. Continuing in this concrete style, we can change the square procedure to let us draw squares of different sizes. All we have to do is edit the box named square to say that square takes an input named size, and that instead of going forward 300, it goes forward by that size. Now when we go back to execute square, Boxer tells us that we need to specify size as an input. This time, let's fill in 200. When we mark and execute this, we get a square that fits inside the original 300 size square. Now that we have a working square procedure, we're no longer concerned with the details of how it works. So we can ask Boxer to shrink the box named square so we can go off and work on something else. For example, we can use square as a building block in another procedure that will draw a design. This procedure repeats 6 times a box which goes forward some, turns, then it draws a square, turns some more, goes forward again, and turns again. Now we can clear the screen again and run design to see what the design looks like. We've seen how we can use boxes to group commands into procedures. Now I'd like to show you how we use boxes to structure our computational world and divide it into different parts which may have different characteristics. Let's make a box that we'll call instant. When the box appears on the screen, we'll go inside it and expand it so that it fills the entire screen. In this box, we'll define a few procedures. The first procedure specifies that whenever we hit the Control F key, the turtle should go forward 200 steps. Similarly, hitting Control R will turn the turtle right 90 degrees, and Control C will clear the screen. Now we can use these instant effect keys to move the turtle. We can add some text to the box as documentation. To do this, we simply type the text in the place where we want it to appear. You can always add things to a Boxer environment simply by typing them, whether adding new text or new procedures. For example, someone who was using this instant box could add a key to turn the turtle to the left just by typing in the procedure. Now we'll exit the instant box and see it as part of the larger structure. Whenever we are inside the instant box, the instant effect keys will be active. Outside the box, these definitions will have no effect. Instant is a very simple example of how we can make a special world just by putting some information in a box. Now we'll go on to see examples of more elaborate worlds, which are constructed in just the same way.
One of the most important features of the Boxer environment is that it allows you to mix text and programs in a flexible way. I've been using this to design an interactive workbook for exploring the physics of orbital mechanics. Here's a top-level view of the workbook. I've used the box structure to organize the section of the book so that this view, with the sub-boxes shrunk, shows us a table of contents for the entire book. Let's enter the section on simulations. This box is an environment that contains a simulation program that we can run. The simulation shows a planet in orbit about a sun and provides commands that let us apply external forces and watch the orbit change. The first sub-box deals with a basic part of the simulation. To set up an orbit, we use the init command, and the book provides a sample call to init, which we can mark and execute. This draws the sun and the planet in their initial positions. Now we can start the planet moving. We can also show a trace of the orbit. As we can see, the initial choice of inputs to init produces a circular orbit. We can change the shape of the orbit by using different inputs to the init command. One easy way to do this is to take advantage of the fact that Boxer lets us edit anything that appears on the screen, so we can go back to the sample call and change it. Having changed it, we can mark and execute the line again and get a different orbit. One of the most important points about these workbooks is that the reader can extend them to try examples that were not provided by the person who wrote the book. This kind of extensibility frees people's imagination and curiosities to try variations on the material that they are working with. I'm going to show you an interactive workbook that I've been developing. This workbook explores various models for animal behavior. It does this by developing procedures which simulate these models and by letting you use the procedures to study the models. This top-level view shows the workbook divided into its main parts, which have to do with models for random animal motion, motion based on smell and sight, and animals chasing other animals. In turn, each of these parts is divided into subparts. The part on sight has subparts for one-eyed animals, two-eyed animals, and animals which only sense the intensity of light. Let's take a look at the simplest model of animal motion, random motion. This part of the workbook uses a model of random motion based on the procedure called walk. Walk simulates random motion by making the turtle repeatedly go forward a random number of steps, and turn through a random angle. The walk procedure takes as inputs 2 sets of bounds, which specify the ranges over which the forward distances and turning angles are sampled. The procedure works by repeating 40 times a forward step followed by a right step. Besides the walk procedure itself, this box also provides a sample call to walk, which we can edit to try different values for the forward and turning bounds. We do this the same way we edit anything else in Boxer. We fill in the sample call with bounds for the forward step and bounds for the turning angle of, say, -30 and 30. Now we mark the call to walk and execute it. We see the turtle moving in a random path. We could now explore variations on these random paths by going back and editing the call to walk to specify different ranges. But since Boxer gives us the ability to edit anything that appears on the screen, we are free to explore in a more open-ended way. We can, for example, change the walk procedure itself. Here, we'll make a very simple change to decrease the number of times that the basic step is repeated. Now, we execute the same call to walk as before. And we see a shorter path drawn.
In addition to interactive workbooks, we have been using the Boxer system to develop what we call personal data management systems. Our idea here is to build flexible systems that people will be able to tailor to their own needs. The reason we believe people will be able to do this is that the basic framework supplied by Boxer already provides much of the functionality needed by data management systems.
Here, for example, is a miniature database which might belong to the grader for an undergraduate course at MIT. Each of the 3 boxes is a record for an individual student, containing the student's name, some administrative information, and a record of the student's grades. I can expand the sub-boxes in a record to show the information in more detail. Now, I can shrink them back again. To add another student record, I could make a new box by typing it in the ordinary way. But to make this common operation easier for me, I've included a special purpose procedure called New Student. This gives me a template for a record, which I can edit to fill in the information. Here again, I use the same editing operations as always when changing something on the screen. When I finish typing this new information, I can shrink the sub-boxes and see that I've added a new student to the database. Now, I've shrunk the entire database and it appears as a box called Students. Besides just looking at boxes and changing them, Boxer allows me to manipulate boxes as data structures. Now I'm going to scan through the database, searching for records that satisfy a certain pattern. The pattern is a box that I've called High Scores, because it identifies students with high scores on their quizzes and homework. The stars here mean that there should be no restriction on the information in the first 2 parts of the record. In the grades part, however, I've specified a restriction which says that in order for the student to pass through the filter, the homework average must be greater than 8. And I've restricted the quiz average to be greater than 75. One thing I might want to do is to write a letter to the instructor of each student with high scores. I can do this using a procedure called collect. The prompt shows that collect needs 3 inputs. The first input is the database I want to use. In this case, the students box. Next comes the pattern to use in filtering the database. Here, it is high scores. The form input specifies a form to be generated using the information in each record that passed the filter. So, I'll put a box here, expand it, and type my letter to the instructor. The question mark before the instructor specifies that the instructor's name should be filled in with the information from the record. Now, I continue typing the letter. And here it is, complete. Here, I'll actually execute the collect. This yields a box with 2 letters in it, because in my database, there were 2 students whose records passed the filter. I'll expand the first letter to look at it. And I could continue to work with this letter and manipulate it the same way as anything else on the Boxer screen.
We've seen how Boxer can be used as a simple programming language, as a new medium for designing such things as interactive texts, and as a simple database system. And the interesting thing is how many of the functions that we needed in order to do these are subsumed automatically by the basic principles of concreteness and by the structure supplied by the boxes. What we're trying to do here is to design a general-purpose system not for professional programmers or specialists, but one that ordinary people will be able to use in order to do very many different things because they feel that they understand and have control over it.